In this video, we're going to talk about conic sections, which are these basic curves, ellipses, parabolas, and hyperbolas. So perhaps we've graphed some of these in the past. Hey, there's an ellipse, there's a parabola, there's a hyperbola. We're going to review it today, or talk about them, from a slightly more abstract, a more geometric viewpoint, to try, I hope, to deepen our understanding of such curves, like how can they arise, how can we describe them, and how much freedom do we have in describing them. A motivating question for this video might be, how come when we draw parabolas, we almost always draw them opening up along the y-axis, maybe sometimes along the x-axis, but almost never along any other line? If you find that question vaguely interesting, you may find this video vaguely interesting. So, I'm guessing most of you are working at a desk. I want you to imagine that you're holding a magic cone which can come up through the desk. So if you hold it straight underneath the desk, the cone will intersect your desk in a circle. And if you move the cone up and down, you can get a bigger or smaller circle. If you rotate the cone around the axis of symmetry, well, nothing changes. What else can you do? Let's draw some more pictures here. Imagine that you tilt the cone. You tilt the cone off to one side, then what you'll get, the intersection of the cone with your desk, is an ellipse, a squished circle. What if you kept on tilting it? Keep on tilting it some more, and I want you to imagine that it's like a double-sided cone, so you have two ends of this cone. So let's tilt the cone and see what happens. Tilt, tilt, tilt. You get wider and wider and wider ellipses until finally, when one edge of the cone is parallel with your desk, something interesting happens. The ellipse breaks, and now you get a parabola. You get a parabola, and if you keep tilting it more and more and more, then that bottom part of the cone is going to come up through the desk. And now you're going to have two distinct curves here, two disconnected curves, and there's where you get a hyperbola. And that's it. What other curves could you get? Well, if you kept on tilting, then the other side of the cone would become parallel with the desk, and you'd get a parabola on the other side. If you kept on tilting, you'd get an ellipse. Now, notice that with the ellipse and with the hyperbola, you have some wiggle room, which means that, if you tilt just a little bit, just tilt it a little bit back and forth, you're still going to have an ellipse, or you're still going to have a hyperbola. But with the parabola, where one side of that cone is parallel, there's no wiggle room at all. As soon as you tilt the cone a little bit, you're either going to get an ellipse or a hyperbola. Okay. Now let's imagine that the table, your desk there, is the XY plane. So here's your table, and you just put some coordinates on it. Maybe you do it like that, or maybe you do it like that. It really doesn't matter, but you just put coordinates on the plane. Now, we'll see, maybe in a future video, that conic sections have equations like this. ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. That's not hard to see once you know the equation of a cone in 3-space, but we'll save that for a little later on. So every conic section in the xy plane can be described by an equation of this form, and an equation of this form gives a conic section in the xy plane. Note that it's a quadratic equation in the variables x and y with 6 coefficients, a, b, c, d, e, and f. Think of these coefficients as parameters. So if you pick 6 numbers for a, b, c, d, e, and f, you'll fix the equation and you'll get a very particular curve, a particular conic section. And if you change any one of those numbers around, you'll change the conic section a little bit. So we sometimes use the phrase degree of freedom to indicate a parameter. So you might look at this and you say, we have 6 degrees of freedom, 6 ways of wiggling around the conic section, 6 coefficients. But we need to be careful. If you multiply that equation in the red box by any non-zero number, you'll get on the surface a different equation, but because the right-hand side is 0, it'll have exactly the same solution set, the same numbers x and y that make the equation true. The equation y equals x squared and 2y equals 2x squared both describe exactly the same parabola. So instead of 6 degrees of freedom, because we can rescale, we only have 5 degrees of freedom. At least one of A, B, C, D, E, or F has got to be non-zero in order to have an equation that's not just 0 equals 0. So we can rescale. So if, for example, if a is non-zero, just divide both sides of your equation by a. And here's what you get. You'll just get a leading coefficient of 1, so you get x squared, and then other coefficients like this, where, you know, b is big B over big A, etc. So there you'd have the 5 degrees of freedom. Now let's see how this idea of 5 degrees of freedom relates to the pictures here. Okay, well, look at the ellipse maybe. Now you could slide the ellipse around in the x direction or in the y direction. So you have 2 degrees of freedom by sliding a curve around on the table. You can also rotate a curve on the table. There's another degree of freedom. You could raise or lower the cone to get bigger or smaller curves. There's another degree of freedom. And finally, you can tilt the cone, as we've been doing. Tilt it to get these different curves. So, just to recap here, you could translate in the x direction. That will give 1 degree of freedom. You translate in the y direction. That will give another. You can rotate in the xy plane. You can raise or lower the cone, or you can tilt. 5 degrees of freedom. So you might hear something like 5 points determine a conic. If you were to, you know, just Google conic sections or something, you might see that 5 points determine a conic. Now, if you look at these first 3, translation and rotation, they don't affect the shape or the size. They only affect the orientation of the curve. The 4th, raising or lowering the cone, affects the size, and it's tilting the cone that is really, really interesting. Tilting the cone determines whether you have a parabola or an ellipse or a hyperbola. Now let's suppose that we don't really care so much about the orientation. We're really just interested in studying these curves according to their shape or their size. So we'd like to imagine just being able to slide the curve around on the table and rotate it to put it in a position, you know, say like right in front of us so that we can study it. Well, by doing that, translating and rotating, we can write the equation of a conic as either ax squared plus ey equals 0 or ax squared plus cy squared plus f equals 0, one or the other. So in the first case, you could rewrite this to be y equals little ax squared, where little a is minus big A over e. And in the second case, you could rewrite it like this. Ax squared plus by squared equals 1, provided, of course, that f is not 0. So in the first case there, you would have a parabola. We recognize that as the equation of a parabola. In the second case, you could either get an ellipse or a hyperbola. Let's think about our degrees of freedom for just a moment. With that equation of an ellipse or a hyperbola, we see a or b, so 2 degrees of freedom. We used up 3 degrees of freedom when we translated and rotated to put it in one of these standard forms. So we still have 2 degrees of freedom left. With the parabola, we have 1 degree of freedom left, a. So what happened to the 5th degree of freedom? Well, the 5th degree of freedom is buried in the fact that this equation here gives up parabola, and so you're not allowed to tilt the cone anymore. As we saw, if you tilt the cone, then you'll get either an ellipse or a hyperbola. And these are what you might call standard forms. So if we want to study conic sections, it's enough to study equations of these standard form. Maybe we can boil things down even further, and we'll discuss that in the next video.